Hello friends, welcome back. In the previous video, we looked at some of the most important properties of complex numbers and a few theorems. Let us now try our hand at different problems. So the first one is solve for z in mod z square minus 2iz plus 2c into 1 plus I equal to 0, where c is real. Okay. So for this kind of question, let us write the value of write z as a plus I, and let us substitute it in the equation, right? So the equation now is mod z square is a square plus b square minus 2I into a plus ib plus 2c into 1 plus I, right? Now let us segregate. First let us expand the bracket and then segregate the real and imaginary parts. I into I is I square, which is minus 1, this becomes 2b, then 2c plus 2ic, right? The real part now, that should be separately 0 and so should be the imaginary part, right? So the first equation we get is a square plus b square plus 2b plus 2c equal to 0, and the imaginary part is minus 2a plus 2c is equal to 0. Right? Since the right hand side was 0 in this equation, we can write this way. Now, from the second one, from the imaginary part, we get that a is equal to 3. Right? So let us put this in the first one, and we get c square plus b square plus 2b plus 2c is equal to 0. So b square plus 2b plus c square plus 2c is equal to 0. Now let us solve for b. So b is actually minus 1 plus or minus root of 1 minus 2 plus or minus this 4 minus 4 times c squared plus 2c by 2. Taking 2 common, we get minus 1 plus or minus 1 minus c squared minus 2c. Right? Now, they have said that now b should be a real number, right? Because I is already written, b is the imaginary part, that means b itself is real. IB makes it completely imaginary. So, in that case, this term should be positive, so that it is the square root of a positive number. Well, that means 1 minus c squared minus 2c. Well, this should be greater than 0, right? Now, solving this, we get that c belongs to minus 1 minus root 2 minus 1 plus root 2, right? So this will be the range for c, so that 1 minus c squared minus 2c is greater than or equal to 0, right? Now once that is written, now we can write down our z. Our z is the real part is nothing but c, and the imaginary part is I times minus 1 plus or minus 1 minus c squared minus 2c. Right? So this is a complex number. Okay. The second one, find real theta such that 3 plus 2I sin theta by 1 minus 2I sin theta is equal to purely imaginary. Is purely imaginary. Okay. Now, what do we do for this kind of question? Now, since we have to find out the values of theta, what we will do is we will first simplify the expression, right? So, let's call this as z. Z is 3 plus 2I sin theta by 1 minus 2I sin theta. See that the numerator, the denominator is actually a complex number. So, we will first try to make it real. So, how do we do that? We multiply it with its conjugate, which is 1 plus 2i sin theta, right? Now that gives us, expanding, we get 3 minus 4 sin squared theta plus 6i sin theta plus 2i sin theta by 1 plus 4 sin squared theta, which can further written as 3 minus 4 sin squared theta plus 8i sin theta by 1 plus 4 sin squared theta. Now you see that for this, our expression has now been reduced to a form where the real part is just 3 minus 4 sin squared theta by 1 plus 4 sin squared theta, and the imaginary part is 8 sin theta by 1 plus 4 sin squared theta. Right. Now the question says, we have to find the real theta such that it is purely imaginary. That means there is no real part, and that means that the real part must be 0. Hence, 3 minus 4 sin squared theta by 1 plus 4 sin squared theta. This is equal to 0. Now the denominator is always positive, so only the numerator can be 0. That means sin squared theta is equal to 3 by 4, or sin theta is equal to plus or minus root 3 by 2. Right? Now we learned in the previous videos how to find out the general solution for this theta. Because they have asked for just real theta, we will have to write the general solution. And since it is plus or minus root 3 by 2, we can write this as n pi plus or minus the principal angle is pi by 3. So theta is n pi plus or minus pi by 3. Right? For just plus root 3 by 2, it will be plus minus 1 power n pi by 3. For negative, it will be minus of minus 1 power n pi by 3. Combining both of them, we can just write this as n pi plus or minus pi by 3. Okay. Now the third question. Find the square root of x square plus y square plus y square by x square minus 1 by I x by y minus y by x minus 9 by 4. Alright. Okay. So what do we do for this kind of question? Now let us first write the required square root as a plus ib. Right? So suppose a plus ib is the square root of this number. So the square of this must be equal to now minus 1 by I. What is I? I is square root of minus 1. So let us just multiply both numerator and denominator by I. So I square in the denominator gives us minus 1, multiplies with the minus 1 already there and makes it plus 1. So it is just I. It's just written in a fancy form. Don't get confused, it's just I. Right? Now equating the real and imaginary parts, you get right? This is for the real part. For the imaginary, we have now this can further be written as x squared minus y squared by xy. Hence, now let us solve these two equations. So b is nothing but by 2a into xy. Right? Let us substitute this in the above equation. So a squared minus x squared minus y squared whole squared by 4a squared x squared is equal to x squared by y squared plus y squared by x squared minus 9 by 4. Right? So a squared we just let's multiply throughout by a squared, so I have a power 4, and then this is x power 4 plus y power 4 minus 2x squared y squared by 4 x squared y squared is equal to x squared plus y squared by x squared minus 9 by 4 into a squared. Right? Now, so this is so we have arrived at a quadratic equation in a squared, solving which we will get the values of a squared. Now, taking the square root, you will find a, and once you find a, you can just substitute b using this formula, and hence you can find out the square root of the number, because the square root is just a plus ib. Right? The final answer is plus or minus x by y minus y by x plus I by 2. This is the final answer. The square root of the number is just x plus y minus y, x by y minus y by x plus I by 2. So the next question now. If x is equal to minus 5 plus 2 times root of minus 4, find the value of x power 4 plus 9x cube plus 35x square minus x plus 4. Okay. Now, we know that I is equal to minus root of minus I, minus 1. Right? Now, x is nothing but minus 5 plus 2 times. Now, root of minus 4 can be written as root 4 into root of minus 1. But root 4 is 2 and root of minus 1 is I. This is just 2 into 2i. It is equal to 5 minus 5 plus 4i. Right? So this is our x. Now let us find out what is x square. X square is just square of this minus 5 plus 4i whole squared, which is equal to 25 minus 16 is 9 minus 40i. X cube is 9 minus 40i into minus 5 plus 4i, right? X squared into x. Okay, so this is 9 into minus 5 minus 40 into 4, which gives me 110 plus 236 i. Now x power 4 can be cleverly written as squared of x squared, so it is 9 minus 40i squared, which is equal to minus 1 by 19 minus 720i. Right? Now that we know the form of all x squared, x cube and x power 4, we can just substitute in the expression and find out the value of the expression. Right? Therefore, substituting all the values, right? So now it's just the addition of five different complex numbers, which finally gives us the real part as minus 160 and the imaginary part as 0. So it's actually just a real number, hence the value is minus 160. Right? So this question, the expression may look a bit scary, but the procedure is very simple. You just have to find out the forms for all the different complex numbers x squared, x cubed and x power 4 and just substitute them in the equation. Okay. Now quick one. Show that mod of 2z bar plus y into root 2 minus I is equal to root 3 into 2z plus 5. Right? Okay. This question is actually this is a conceptual question. We know that z mod of z is equal to mod of z bar, right? So let this be a z, the first expression, and the mod of that should be equal to the modulus of its conjugate, right? So this is equal to 2z bar plus phi into root 2 minus I is equal to the modulus of the whole thing, 2z bar plus phi root 2 minus I whole mod is equal to, now whole mod is actually this can be written as the argument can now be written as say the conjugate of the first one into the conjugate of the second. The conjugate of first is 2z bar plus phi into root 2 minus I mod conjugate. The conjugate of 2z bar plus phi. Note that remember double conjugate is always positive. Gives back the original, right? So z bar conjugate will z bar conjugate will give us z, whereas phi and 2, the coefficient 2 and here the number phi, both of them are just real numbers. The conjugate is the same number, right? So we get 2z plus phi. Now the conjugate of root 2 minus I is root 2 plus I. Now I evaluate what the modulus of root 2 plus I. Root 2 plus I, the modulus is 2 root of 2 plus 1, which is root 3, right? And I can always take that out with a positive sign, and what is left is 2z plus phi, which is required in the equation, in the answer, in the question, right? So this is how, just using this property, we find out that we solve, we prove it, right? Okay. Now, for this question, if alpha and beta are roots of the equation x squared minus 2x plus 4 equal to 0, find alpha power n plus beta power n. Okay. Now let us first solve for this equation. So x is equal to 2 plus or minus 4 minus 16 by 2, which is 2 plus or minus 12, this is minus 12, square root of minus 12, which is 2 root 3 into I by 2, right? Now remember, omega and omega square interchangeably could be written as, okay, let's forget that, let's just write this way. This can be written as 1 plus or minus root 3I, right? So let alpha be equal to 1 plus root 3I. Now writing this in the Euler form gives us 2. The cos is nothing but 1 by 2, which is equal to the 60 degrees of pi by 3, right? So e power I pi by 3. The other root, there is nothing wrong in choosing them as one specific root. Since these are the general formulae, this will not hurt our question here, right? And beta is 1 minus root 3I. So this is equal to, right? So first we solve for x we get this as 2 plus or minus 2 root 3I by 2, which is 1 plus or minus root 3I. Writing that as in the Euler form, we get this as 2 into e power I pi by 3. We just take 2 common and then we get 1 by 2 plus root 3 by 2I, which can be written as e power I pi by 3. Right? Now what we require is alpha power n plus beta power n. Right? So alpha power n plus beta power n is equal to 2 power e power I pi by 3 whole power n plus 2 e power minus I pi by 3 whole power n, which is 2 power n e power I n pi by 3 plus 2 power n e power minus I n pi by 3. Now let us just simplify this. So we get 2 power n into e power I n pi by 3 plus e power I minus n pi by 3. Right? So which is 2 power n into 2 into now. Now let us just expand this. Now what is e power I n pi by 3? Actually, you can directly write this as you can directly simplify this, but because this is e power I n pi by 3, this is just the conjugate, right? So a complex number plus its conjugate gives us the twice the real part, right? But I'll just expand it to actually show that. Anyway, so this is cos n pi by 3 plus I sin n pi by 3, which is cos of minus n pi by 3. We know that is equal to cos of n pi by 3, and I have minus I sin of n pi by 3. There comes a minus here because sin of minus n pi by 3 is minus sin n pi by 3, right? So the imaginary part actually cancels, and I have 2 power n cos for n pi by 3 into plus cos of n pi by 3 is 2 times cos n pi by 3, or this is 2 power n plus 1 into cos of n pi by 3. So this is our answer. We just have to find out alpha and beta and use the Euler formula, and later on the De Moivre's theorem to just simplify the expression, and we get this as 2 power n plus 1 into cos of n pi by 3. Right. Okay. Now if mod of z is equal to 2, show that the points representing minus 1 plus phi z lie on a circle. Okay. Now the question says, the question is concerned about the points represented by minus 1 plus phi z. So let us write that as z1, right? Z1 is equal to minus 1 plus phi z. But we can always write this as z1 plus 1 is equal to phi z. Why I do this is because I have been given the value of mod z, right? So I write it this way, and then I just take the modulus on both sides. Z1 plus 1 is equal to phi times actually mod of phi z. Since phi is a positive number, and anyway it's just a number, real number just comes out, and we have phi of mod z. But what is mod z? Mod z is always 2. Hence this is phi into 2, which is 10. Right? So I have equation z1 plus 1 mod of that is equal to 10. Now what does this mean? This means that this can now be written as z1 minus of minus 1 into mod of this is equal to 10. Now if you remember, while writing the distance between 2 points z1 and z2, we write that as z1 minus z2 mod, right? So what this in other words means that let z2 be a point minus 1, that means minus 1 comma 0 or minus 1 plus 0 I. This is let this be our z2. So the distance of the point represented by minus 1 plus phi z or z1. So the distance between z1 and minus 1 is always 10, right? Modulus is nothing but the distance. The distance is always 10, but that means that it is a circle, right? Hence, we are just supposed to bring this into this form, and hence we can write this as hence z1 represents a circle. Right? Now further, minus 1 actually is the center, right? And 10 is the radius. Okay. The next one. If z is equal to 2 plus t plus I times root of 3 minus t squared, where t is real and t squared is less than 3, show that z plus 1 plus z minus 1 whole mod is independent of t. Also show that locus of z is a circle for different values of t and find its center and radius. Okay. Right. So z is equal to 2 plus t plus I times root of 3 minus t squared. That means z plus 1 is equal to 3 plus t, right? Only the real part, only one gets added to the real part. So I have the imaginary part is just like that. No change to that. And similarly again here, plus I times 3 minus t square, right? Now mod of z plus 1 by z minus 1 is nothing but mod of z plus 1 by mod of z minus 1. Right, so let me find out the separate modulus. This is equal to 3 plus t whole squared plus 3 minus t squared. Right, expanding which we get that t squared actually gets cancelled because of the minus sign, because of minus t squared here. So I have 3 squared, which is 9 plus 3, which is 12 plus 60. And similarly, z minus 1 is 1 plus t squared plus 3 minus t squared, and this is 1 plus 3, which is 4. T squared cancels again, and we have 2t. Right? So I see that z plus 1 by z minus 1 is nothing but 12 plus 60 by 4 plus 2t. Now we see that we can take common 2 plus t, right? So let us take 2 plus t common here. Actually, another 2 becomes common, and so we see that the mod of z plus 1 by z minus 1 is nothing but 3, and that is what is asked to prove, right? So we show that this is independent of t, right? The next part is show that the locus of z is a circle for different values of t and find its center and radius. Okay. Now again, we try to manipulate z here. And how do we do that? Now this actually will come only for practice. More and more solve more and more questions, and you'll see how you're supposed to do for a specific question. Right? So I see here that the root of 3 minus t squared, when squared will give me 3 minus t squared. Now to make it independent of t, what I should do is just subtract 2 on both sides, and I have t plus I times 3 minus t squared, right? Let us take mod of this. So mod of z minus 2, so this is z and this is 2, that is equal to t squared plus 3 minus t squared, right? So the t squared cancels and we have only 3. Z minus 2 is equal to 3. Now what does this mean? Now, I'm sorry, this is z minus 2 squared, right? Z minus 2 is t plus I times root of 3 minus t squared, or z minus 2 whole squared is equal to this, or z minus 2 is equal to root of 3. Now what this means is, the center, now again from the previous question we know that this is the equation of a circle, right? And the center is 2, that means the imaginary part is 0, or it should be 2, 0, and the radius is root 3, right? So we're supposed to prove that the locus is a circle, and and to find its center and radius, the center is 2, 0, radius is root 3, right? Okay, so the ninth question now. Solve for z minus 12 by z minus 8i whole mod is 5 by 3, and z minus 4 by z minus 8 is equal to 1. Okay. Now in this question, what I do is, I'll first write z as x plus iy, right? So, let us take the second one, because the second one actually has only real numbers on the other side, so z minus 4 and z minus 8, because here there is 8i, and moreover the constant on the right hand side is only 1 for the second equation. So I just consider the second equation here first. X plus iy minus 4 plus divided by x plus iy by 8 whole mod is equal to 1. Is equal to x minus 4 plus iy. Whole mod of this is nothing but equal to x minus 8 plus iy, right? Now we can actually square this and let us find the mod. Let us take the square on both sides. That gives us y squared is equal to x minus 8 plus y squared, right? Now the y squared just gets cancelled and we have x minus 4 squared whole squared equal to x minus 8 whole squared. Now without solving also you can see that this is equal only when x lies between 4 and 8 or x is equal to 6, right? You can actually do rigorous calculation also, but since this is a very simple one, x minus 4 squared is equal to x minus 8 whole squared. Now just taking the root and you can see that 4 plus 8 by 2 gives us 6, right? Now let us put it in the first equation. So I have z minus 12 by z minus 8i is equal to pi by 3. Now z is nothing but 6 plus iy. I know that x is always 6. So 6 minus 12 gives me minus 6 plus iy, and I have 6 plus y minus 8 I times, right? So let us square both sides and cross multiplying we get 6 squared plus y squared into 3 squared, which is 9, is equal to 25 into 6 squared plus y minus 8 squared, right? So this 9 into 36. 6 squared is 36 into 25 is 900 plus 25 into y minus 8 square, right? Solving this equation, we get that y is equal to either 8 or 70. These are the possible roots of the equation. Now, both of them are completely fine. So we'll just, we are supposed to actually back check these kind of questions, because sometimes we may get some extra solutions which may not be correct for the specific question. But however, for this one, 8 and 17, both of them are perfectly correct. So we get that our answer is, it's not 8, it's actually 6. 6 plus 8i or z is equal to 6 plus 79. Both of them are perfectly fine. Right? So these are the solutions to our equation, our question here. Okay. Now for this question, if mod of z is greater than equal to 3, determine the least value of z and the corresponding z. Right. Oh, I'm sorry. The question is not finding the least value of z. It is finding the least value of z plus 1 by z. Right. So now for this question, this is a classic case of inequality, right? We're supposed to find out some kind of inequality. We have to invoke some kind of inequality and find out the least value. That will be the inequality. That will be equality in that case. Moreover, we're supposed to find out the value of the corresponding z also. So look carefully. I'll try to write it this way. Right. So plus 1 by z, I'll write that as z minus of 1 by minus z. Right? Minus makes it positive. So we are actually, this is correct. Now you know that z1 minus z2 is greater than equal to mod z1 minus mod of z2. This is z2. Okay. So Z1 minus Z2, mod of that is always greater than equal to mod of Z1 minus mod of Z2. This actually comes from triangle inequality, right? Suppose Z1 and Z2 are two sides of the equation, and suppose this is this way. Z1, Z2, okay? So this will be Z1 minus Z2, right? The third side will be Z1 minus Z2. So that Z2 plus Z1 minus Z2 gives me Z1 back, right? Now we know that in a triangle, the sum of two sides should be greater than the sum of the third side. The distance is nothing but the side, right? So writing it that way, so I know that Z2 plus mod of Z2 plus mod of Z1 minus Z2 should be greater than Z1. Hence, this should be greater than Z1, right? Hence, taking it to the other side, we get this. Now we should take a modulus again on the right hand side. This modulus you're supposed to take, because mod of Z1 minus mod of Z2 could be negative, right? So to take that possibility out, we should take a mod, right? So let us use this inequality, a very useful and powerful inequality. So Z minus 1 by mod Z. Now this should be greater than mod of Z minus mod of. Now I can take 1 by minus Z as my Z2. So this is 1 by minus Z, right? But this is nothing but the second part. Let us now see what the second part means. Now 1 by minus, first of all 1 by minus Z is nothing but 1 by Z, right? Mod of that, minus sign doesn't matter. And moreover, 1 by mod of 1 by Z is nothing but 1 by mod Z. So I can write this as this, right? Which is nothing but, now I know the values of Z. The minimum value is the minimum value is 3, and this is 3 minus 1 by 3. Now the modulus is actually not important because this is always positive, and this is equal to 8 by 3. So we see that the least value is equal to 8 by 3. Let us now look at the second part of the equation. Okay, so we are supposed to find out the corresponding Z, right? So let us now write Z in the polar form. Z is nothing but E power I theta, R times E power I theta, right? Right. So Z plus 1 by Z now is equal to 8 by 3. Now let us expand everything. Substitute this 1 by R bar. Okay, this is R E bar I theta, 1 by R E bar minus I theta. Right. Now let us look at the question. The question says mod Z should be greater than or equal to 3. For the least value, it's pretty obvious that the value here R should be equal to 3, right? So putting R is equal to 3, we get that this is nothing but 3 times E bar I theta plus 1 by 3 E bar minus I theta. Right? Now E bar I theta is nothing but cos theta plus I sin theta. E bar minus I theta is cos theta minus I sin theta. That gives us 10 by 3 cos theta plus 8 by 3 sin theta. This is equal to 8 by 3. Let us just take the square on both sides. That gives us 10 by 3 squared cos squared theta plus 8 by 3 squared sin squared theta. This is equal to 8 by 3 squared. Right. Now, so this is nothing but an equation is cos squared and sin squared. Let's use the universal identity. Sin squared theta equal to 1 minus cos squared theta. And that gives us so I just take my 8 by 3 squared to the right hand side, and this gives me 8 by 3 squared sin square theta minus 1, which is minus of cos square theta, right? So minus cos square theta into 8 by 3 squared, right? So the coefficient now is 10 by 3 squared minus 8 by 3 squared, which is something non-zero, and hence cos square theta is 0, hence cos theta is 0, hence theta is equal to plus or minus pi by 2, right? Hence we see that our z, which is r e power I theta, which is nothing but 3 times e power plus or minus I pi by 2, right? This on simplification gives us z is nothing but 3i or minus 3i, right? So we see that the corresponding z is actually 3i or plus or minus 3i. Substituting this, we can easily see that yes, that is actually that actually gives us the value of 8 by 3, which is the least value. That concludes the lecture series on complex numbers. Thank you.